Okay. So, um, yeah, so I'm going to start with kind of a recap. Let me know if everyone could see my like slides. Okay, cool. So, yeah, I'm going to start with like a recap of what we were talking about last week, just for anyone who wasn't here last week, and just kind of like, as a recap. We talked about how like MoE models decouple your parameters and flops. Um, it allows you to make a dense model that has, way more parameters, or it allows you to make a sparse model that has way more parameters than a dense model, and sort of conditionally pick out parameters for each layer with a routing mechanism. And yeah, this is basically like controllable sparsity. So while an MOE model might have more parameters than a dense model, you're only activating like a small fraction of those at each inference pass. And we basically talked about like, okay, why do we want this? And MOE models, in some cases, train faster and also outperform dense models per flop. So you could have the same speed, the same inference speed, but you would use more memory. You would have the same inference speed, but you would have like better performance. And to do this, they introduce a bunch of new. They introduce well, the routing mechanism, which I'm going to cover in a few slides, and they introduced an auxiliary loss to make sure that all the experts specialize during training. They also did stuff like add Gaussian noise during training, and yeah, token-wise gating sort of routing function. Um, and for the original MOE paper, they like for each layer you would pick out several experts. You would do kind of like you have like a top K like parameter, which was two or three, and um, you would sort of merge the layers during your forward pass. And since gating networks with softmax like naturally sort of favor a small number of experts, um, you know, uh, this sort of sets up the idea that you could make top K just be one, um, which was like one of the changes that they made in this paper. Um, and yeah, so now you could control, the number of parameters independently from the like the flops they use at inference, and also the flops they use during training. And you can train a model with like a sparse model with more parameters quicker. You know uh, um, it would have better performance than a dense model. So you could sort of you have this like new trade-off between like memory and sort of performance that you didn't have before with dense models. um, and this paper, switch transformers, is basically optimizing like MOE models. It introduces a couple of simplifications to the architecture. Um, it optimizes for like parallelism, and it also has a lot more sort of up-to-date results from training larger switch transformers on the T5 architecture as opposed to, you know, LSTM or like a smaller model. Um, and so this actually gives you a better picture of like how a large MOE model would perform as opposed to like a dense model. Um, and I'm going to start with the architecture simplifications. Um, the first one is, the routing's been simplified to where top K is now one. So for each token, we take the expert with like the maximum probability. And according to the paper, this doesn't have like a big impact on the model performance, but this is good for a couple of reasons. One is just, simpler, but two, it kind of avoids merging like the merging step that you had with several experts. So you're not merging two like too dense layers anymore. Um, and yeah, so this is kind of similar to the original MoE architecture, except you replace your top k equals 2 or 3 with just top k equals 1, so just like an argmax. Um, so as opposed to like during the forward pass, as opposed to a dense model, we have like your X, which has shape, sequence, length, batch size, dimension model. We have the like the routing is a weight, it's like a matrix weight with shape, dimension, model, number of experts, and you also have a list of experts um, that is each like a feed forward layer. So you matrix multiply X with the router, and you get something like the probabilities of each expert with the shape, sequence, like batch size, number of experts, and we basically just want to pick, like along this last dimension number of experts, we basically just want to pick the one with the highest probability. Um, and then that sort of that points to like one of the experts. This is like an index, points to one of the experts, and you use that expert per token to get your output, and you sort of merge them at the end. And this is as opposed to what we did before, which was you would have several expert layers with like their probabilities, and you would sum over or sort of you would merge them together like weighted by their probability at the end. And I have some like pseudocode kind of that does this in PyTorch. Um, you have like a list of experts. You have your switch layer, which is pretty much just a like a linear layer or a matrix. Um, you get your probabilities, then you get your like maximum. Um, this should actually be an argmax, but you argmax over the last dimension. You get your routes, and then you like those end up being your indices going to each expert. Honestly, this looks a little bit complicated, but all it does is you're just like you have a bunch of slices along the like the sequence length dimension, and you pass each slice to each expert. Um, and at the end, you just combine them together into the original shape, which has like the length of sequence length. Um, I'm gonna stop here, and if anyone has any questions, because this part's kind of like important for the forward pass. So I'd like to clear up if anyone has any questions like so far. Uh, well, I think I took it from like papers with code and changed it a little bit to be a little bit easier to understand. But yeah, this part is still a little bit complicated. Um, but yeah, this is just kind of pseudocode. Like this is sort of what it's going to look like. Uh, expert expert output. Mm, yeah, that probably shouldn't be there. Huh, okay, so yeah, I mean, you like you're indexing with your list of like maximum probability experts. You're indexing into the sequence length dimension. You get a list of slices, and then you pass each slice to like each expert that's responsible for that slice, but they don't have to be like contiguous. So, for example, one slice could be like the indices like 1, 2, 4, like 10, 12. The second one could be like 3, 9, 7. So yeah, they're just like a list of slices, and you pass them to each expert. Um, okay, so there's there's like like a little bit like there's some more code that you have to do for the inference to handle the like capacity factor. And the capacity factor is like each token is routed to the expert with the highest probability, but each expert also has a capacity factor in tokens. And if you're feeding more tokens than the capacity factor of the expert, then they'll just be dropped. Um, so like during each forward pass, it's not guaranteed that each token like is kind of gets fed into an expert. But in practice, like the number of tokens that are actually dropped like after training is very small, and um, it's sort of it's also like the exit like part of the reason for the auxiliary loss is to make sure that the number of dropped tokens is like very low. Um, but the positive is this basically forces each expert to have like a certain number of tokens that they're responsible for, if that makes any sense. And so this is like again a way that the authors try to get the experts to be like balanced and prevent like a large percentage of the work being done by like any one expert. And yeah, and so they also talk about how like you could make the capacity factor larger. Like you could it's sort of like by default I guess there's a couple of variables, but by default like this thing we call the capacity factor is 1. And with capacity factor 1, like each expert has the same number of like tokens that they get routed. But with you could increase it to like 1.5, and then like an expert could handle like 1.5. Like for example, one expert could handle 3 tokens while like another one handles 2. So there's like a little bit of leeway there. And then that would basically mean that some other expert would only handle like 1 token, right? Um, and this is kind of a hyperparameter. And basically the authors say that like you could have like higher performance with a higher capacity factor, but then when taking like parallelism into account, if you have each expert running on one device, then you wouldn't want again like a large percentage of the work being done by any one device. Um, and yeah, so that's pretty much the consideration there. Um, and yeah, this is done during well, it's done during inference, but yeah, like any of this code also gets run during training. Um, yeah, so this is like a very like I kind of simplified this a lot. Basically, you loop over your experts, and if the if the length of the indices that the expert is responsible for is equal to or less than the capacity, you just keep going. And then if it's not, then you need like some way of like clipping it or like dropping tokens. So here you basically just you drop tokens up to like this capacity. And just to clear up a little bit of confusion, like the capacity in practice, like there's a capacity factor and then there's the capacity. This variable capacity could be like 64 tokens or something, but then with a capacity factor of 1.5, like the capacity could be man, I'm bad at math. Like 96 or whatever 64 plus 32 is. But yeah, and the yeah, so another sort of like simplification to the architecture is the load balancing loss they basically get rid of, and they just leave the auxiliary loss. So the load balancing loss was basically responsible for making sure that the variance in the expert probabilities was low, like it punished a high variance. Um, and so, like for example, if you have one expert at 99% all the time, and then another expert at 1% all the time, that would be punished pretty heavily. Um, but if we use top key equals one, we don't really need this. Like we kind of want one expert to be selected per token anyway. Um, and so basically the authors only leave the auxiliary loss, um, which like only like it gets added to the total model loss during training. Oh man. And this sort of talks a little bit more about how this auxiliary loss is calculated. Um, you basically do yeah, so you're doing like this might actually be the load balancing. Yeah, never mind. So um hmm, uh, yeah, I mean I guess okay, ignore what I said about the load balancing loss. I'm actually not so sure. But basically the auxiliary loss is you're doing a dot product between the like the router probabilities and like the fraction of tokens dispatched to each expert. And so okay, yeah. So let me rephrase. The load balancing loss was responsible for the variance in the like router probabilities or the expert probabilities. The auxiliary loss is responsible for making sure that the scores for the probabilities lines up with the fraction of tokens dispatched to each expert. Um, and here's some like a kind of pseudocode that again does this. So you basically you save all of your like router probabilities, and you also save your fraction of tokens like dispatched to each expert. In practice, this should be equal to the capacity. Um, and you compute the dot product. So if like the probability is high and also the fraction of tokens dispatched is high, then this is going to be a large number for the loss. Okay, so next I'm going to talk about like a couple of ways that they improve the training. More importantly, or more specifically, the initialization. Um, the authors tried like mixed precision, and it ended up not being very like numerically stable. Um, and the part that wasn't stable, like they determined was the router input. Um, so the way they went around that is like selectively casting the router input to float 32, and then leaving the rest in like B float 16, and then after you compute this router input, you would cast it back down to B float 16. Um, and they also changed the like some of the initialization for just the model. So your normal distribution, uh, I think n is the number of experts and s is the sequence length. Probably should have included that, but the initialization scale is also reduced by a factor of 10. And what's also interesting is that they use like expert dropout instead of regular dropout. So the the like a higher dropout is applied to each like expert linear layer than to the rest of the model. And I think the ratio is like um, it's like I think it's like 15% higher dropout to the experts. Um, and yeah, so these are just a couple of like techniques to like optimize this new architecture for training and especially for like mixed precision. Um, the next thing I'm going to cover is like how they implemented parallelism, because if you think about it, like an MoE kind of adds a new like dimension that you could do parallelism across, which is the expert dimension. So now you would have sort of data parallelism, model parallelism, and then expert parallelism. And here's just a bunch of terms. You have your batch size, um, your the number of cores that you have. So this would be like a TPU core. Um, the number of ways you could do data parallel and model parallel sharding. And then also you have E now, which is the number of experts. And you also have C, which is the expert capacity. Um, and the paper implements the like the architecture in mesh TensorFlow, which is like kind of like a little bit dated. I think the newest implementation is in the like T5X repo, but pretty much it's the same way of doing like parallel sharding. And I think the way that they actually like the way that they explain this with mesh TensorFlow is kind of like easier to understand. So I left like a couple of slides there that are based on mesh TensorFlow. And yeah, so you have your N, M, which are your number of ways for data and model parallel sharding, and then you have your batch size B, and you have your also your like the dimension of each layer. And like first we have data parallelism where um, remember how we have like big N, capital N being the number of ways that you could do data parallelism. I guess this could just be like your number of cores. Yeah. So you would set like the number of like the data parallel dimension to be capital N, and you would set the model parallel dimension to be 1. So essentially, you're running like a new an instance of the model on each core, and then you're sharing the data across cores, and you're incurring a communication cost. Um, sorry, this is model parallelism. So the opposite of this is model parallelism, where your model layers are fully parallel, and then you're doing no data parallelism. So like so there's one like each core is responsible for hosting like a shard of the model, and then you're essentially feeding the same data to like I guess you're feeding one instance of the data to the model, and the model is like fully sharded. Um, yeah, so here you're getting a communication cost because with model parallelism, like for example, if you have something like one layer on each core, then you would need to like do the forward pass for that layer, and then like communicate with the next device that's responsible for the next layer. So this has like a high communication cost. I thought this diagram was pretty useful for how like they represent data and model parallelism. Um, Probably explains it a little bit better than I could, but yeah. So like this shows how the model weights are split across cores and how the data is split across cores. So with data parallelism, you have like one replica of the model on each core. And then you're feeding like a small fraction of the data to each core, and you're sort of doing like a reduce after. With model parallelism, you have you have like a small part of the model weights on each core, but you're feeding the entire data set to each core, right? And you could also do both. So you could do like um, you could figure out like some trade-off that just works for your your architecture for training, where you use both model and data parallelism. And here, the colors that they are basically showing like unique data. So this doesn't get reduced like with the data parallelism. So this is like unique data. And there's you could also do so yeah, so now they add in like expert parallelism where one expert lives on each um uh, like each core essentially. And so this could be like, like each layer, you just select like the expert from each layer, and you would sort of make each core responsible for that expert. Um, I guess across layers. Um, and this is like with data parallelism, you're giving each like expert a fraction of the data, and then you're doing a reduce at the end. And then it gets even more complicated where there's expert model and data parallelism. Um, and essentially, if like I would say if you want to look into how they do like this like 3D kind of parallelism, I would really go into like I would take a look at like T5X, and also DeepSpeed has like a good tutorial on how to do like expert parallelism. Um, but yeah, and so this just talks again about expert and data parallelism. Um, yeah, yeah, yeah. Well, I mean, the way that they did it in mesh TensorFlows, they kind of have like two layers of reduces. So it is like very much a separate dimension. So you would have like um I mean like tensor parallelism they don't even do here, but you can do tensor parallelism with this, like just replace the model parallelism with tensor parallelism. Um, but you would reduce like first across the model parallel dimension and then across the expert parallel dimension. So they want you to think of it as like a third dimension to do parallelism across, basically. Um, yeah, so I guess I could cover expert and data parallelism again because um, I think it's like kind of useful to know. But yeah, it is very much like you said, like model parallelism. So you're allocating like you're allocating uh, b over n across the data dimension to each like core. And for each token per core, you have a router that's like locally assigning to the experts. Um, and after this assignment step, it sends the tokens to either one of these experts. And um, basically, I mean, you yeah. So instead of like a model parallel dimension, you're doing a gather or like reduce across this new like expert parallel dimension. um and yeah, and so again, like I said, this is essentially like a two-stage reduce. I like to think about it as like an inner reduce along the model parallel dimension, then an outer reduce when you're like routing the experts. um and the authors talk about how this like presents a trade-off where you have like you could scale up the number of experts, but you could also scale up the dimension of the model. And each of these like increases the flops per token if you're keeping the batch size constant. So you could go either way. Basically, you could have like a larger model with less experts, or you could have a smaller model with more experts. And that's sort of what the authors tried to figure out, is like, which is better? Is it better to have, let's say, T5 large with like 64 experts, or T5 base, which is smaller with like 256. Um, yeah, yeah, probably just a nicer picture. There's no real reason. Um, yeah, this is like otherwise this is a great diagram. Just the colors make it a little bit confusing because there's like the colors for the data and then the colors for the experts. So anyway, the last sort of section is like the results. The authors will switch transformer like the you know switch transformer is based on T5 like the original switch transformer. Um, and all the experiments in the paper are done on T5. So T5 base, T5 large, and T5 XXL for the base models. And the authors try two kinds of scaling. So the first kind is um, where you use a slightly like both models are very large for the largest two switch models, but one of them has a much larger base model, and the other one has much more experts. Um, like yeah, 64 versus 2000. And Switch XXL has a like much higher sort of inference cost, but it uses about like four times less memory. And then Switch C is like the largest like model, and like the the size of the model in memory comes from the fact that it's just has like way more experts. Um, and like what you could sort of see is like if you keep the number of flops uh, per sequence like constant, then a switch model will outperform like the model immediately above it, or have like comparable results in terms of perplexity on C4 with the model that's like directly above it. So T5 base, switch T5 base outperforms the like dense T5 large. Um, and you can sort of see this here. So you're if you're comparing like switch base to T5 large, the perplexity is lower. You could also kind of make this comparison for like switch large versus XXL, but because XXL is like a big jump in terms of parameters, um, it does outperform switch large a little bit. Um, the last sort of important comparison is between these two approaches, like bigger D model versus more experts, which is switch XXL versus switch C. And the results they basically got was, yeah, like switch XXL does perform slightly better, but it's like it's so much more expensive to do inference compared to switch C. So you're really again making this trade-off, like memory versus your flops. And yeah, yeah, yeah. Well, yeah, I don't. Okay, I guess with flops, yeah, I'm talking more about like um how expensive it is to do inference, basically. And yeah, yeah. So yeah, um, per training sequence, yeah. I think this is like you could replace this with just like some way of measuring like the cost for inference, and it would be pretty much the same numbers. but yeah, I have to take a look at like what they exactly mean. Yeah, this is what they imply. Well, yeah, it wouldn't cost more flops because you're routing to one expert each time. Well, yeah, but basically the point that the authors made was that this was like pretty much like negligible in terms of like, like this um flops number. Yeah. Well, I mean, I mean, you can't use the same definition of undertrained with experts. I don't think you could really use yeah. Yeah. I would say that, okay, I would say this. I would say this. I would say that like you can't necessarily compare it with like chinchilla laws because I feel like the chinchilla laws for like a switch model would be just, way different than a dense model. And just like the routing introduces like a whole new like aspect to how the model works to where like I feel like you can't, just take like a feed forward layer out of each expert and just say like, oh, this is undertrained. I feel like it's kind of like a different kind of model, right, to a dense model. Yeah, I think that'd be a good idea. Yeah. Well, not the attention layers. So the attention layers, well, that's kind of like an implementation detail. But your attention layers, um, like let's say you're doing like an MoE with the linear layers. Um, you have a linear or sort of feed forward block, and then you have an attention block. The feed forward block would just require much more memory than the attention block, and so you could maybe keep the attention block on like one device, but then have like a whole like 4, 8, 16 devices, which you distribute the experts across. Yeah. Yeah, I mean, I would need to take a look at like the implementation. They basically just like focused on how the expert layers specifically are parallelized. Yeah. Yeah, I guess I would want to wait until like reading the scaling laws before I actually talk about like what undertraining and overtraining means, because it is just like a completely different model. Yeah. Do you guys see this? It's like a PDF. Okay. Um, yeah. Uh, well, I would argue that, like first of all, it diverges if you try like lower precision. So I guess you could see why they focused on like the linear layers. Because that basically, this would need, more work. Um, but yeah, I haven't looked into this a lot. So, you know. Okay, I want to wrap this up, and then after that, we could talk a little bit more. Um, yeah, I think I have like a couple more slides. Um, but yeah, so the takeaway is that however you define flops, either for training or inference, your switch transformers like kind of punch above their weight class. Um, and switch base, um, like I said, beats T5 large with like 30% the flops and 10 times the weights. And Switch Large is like, sort of competitive with T5 XXL with, even less flops and 2.5 times the weights. Um, and so you could basically say that, at larger model sizes, well, from their experiment with Switch C versus Switch XXL, you could say that a larger base model will outperform more experts. But you would also wonder, like, is this worth it um, if you're spending, so much more compute? Um, But the authors also noted that larger model sizes introduce training instability. Um, while if you do like a smaller model with a large number of experts, they're stable even at like 1.5 trillion parameters. Um, and so yeah, this is basically a um, uh, like y yeah. I can't tell you like yeah, like I'm not super sure. I would need to like take a look at the reasons they gave, but pretty much like that's just like a rule of thumb is that like you would need to sort of spend a little more time like figuring out how to solve like the training instability if you want to have both a large um, model size and like a large number of experts. Um, yeah, and so the authors like report they talk about how like actually the sample efficiency might be better than dense models, especially for the larger MoE models. But this is kind of like at the end of the paper. There's some notes on that. And Um, yeah, this I would actually need to take a look at again if it's state of the art on C4. Um, this was kind of just like a footnote. I would need to like to take a look again. Um, and the last thing that I wanted to talk about was how the authors actually tried like doing like model distillation. So you would distill switch T5 back into T5 by like using it as kind of like a teacher model, and they were basically able to get a good amount of performance improvement. I think it was like 30% for T5 base um, on a few tasks by just doing this distillation. So you would train a switch transformer first, and then you would train like a distilled dense model. Um, and this could be like a way of sort of preserving, like some of the performance improvements of like a switch transformer, while still having a model that you could fit into memory for inference, like on like a single GPU or that kind of use case. So like consumer GPUs, smaller models, things like that. Um, and yeah, and I also found like a Google Colab, and I'll post all these slides. By the way, I'll share them. But I found a Colab where you could train a switch transformer with like Hugging Face. Um, and yeah, that's pretty much it. That's switch transformers. Um, does anyone have any questions like about any of the slides or just the presentation? Yeah, it is. Well, for their like T5 example with T5 base, then yeah, it is. Like I could actually go into the paper. Like it is a good jump in performance if you're doing the distillation. So I think it's worth doing, especially if you have like a um like smaller model where you could afford to do distillation. Um, let me see. Yeah. Um, well, I think they did use the same amount of steps, but I would need to find it. I mean, I would guess that they would because they sort of make a big deal out of how it's sample efficient. Um, uh, like yeah, I mean, I wouldn't so much. I guess personally, I wouldn't care about like how many steps that they take like in the distillation, but I would care about how like if they take the same number of steps for training the T5 versus the switch. Um, okay, yeah, yeah, okay. So um, there we go. So you could train a distilled T5 base model, and you would have like a pretty big performance improvement on super glue. Um, okay, cool. Any more questions? Guess that's a no. Uh, okay. Yeah, I mean, like the results I think are pretty useful, but you know, it is on like T5, and I think there's a whole bunch of like stuff on like MoE scaling laws, um, that's I think is like worth covering. Well, yeah, this is just a Google thing. Uh, actually, so yeah, yeah, you could replicate all the results in the T5X repo, I think. Like, I'm not sure about these two larger ones, but I have like I've looked at the code for like you know switch transformer for like T5 switch transformer stuff like that. So you could definitely replicate those. Yeah. So then I guess that would yeah, cool. Yeah, and then I also know that like DHP has a like an MoE implementation. Um, so yeah, all right, cool. Yeah, I think oh, well no, it's not in this paper. Um, I think I've heard about like hierarchical MoE from like NVIDIA recently, but I'm not sure if that's true. But I think like there are there might be actually like architecture uh like you're training on GPUs and you have like interconnect. There might actually be real reasons to do like hierarchical like MoE, but I would have to like sort of read about that a little bit to figure out why. Makes sense. Okay. If no one else has any questions, then I'm gonna wrap this up. Um, yeah. Thank you. Thanks everyone. Um, thanks for the chat emojis. Yeah.